Hello there, calculus fans, and welcome to section 11.5, where we talk about alternating series and absolute convergence. So the convergence tests we've looked at so far apply only to series with positive terms. Now we're going to learn how to deal with series whose terms are not necessarily positive. And an important example of this is the alternating series. An alternating series is a series whose terms are alternately positive and negative. So we've got an example here. This one may look familiar. We've seen a series sort of like this, but the series that we looked at had all pluses. Now this one alternates. You got a 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. So they alternate. And then you can see up here they've got this part here that's going to make the signs change, because whenever this -1 is to an even power, you'll get 1. But whenever it's to an odd power, you get a -1. And this particular series is the alternating harmonic series, which converges, as we will see. We'll see in a few minutes here. But if you notice it, it's the alternating harmonic series. The harmonic series we're familiar with, where they're all pluses here, and where there's just a 1 here. But this one, when this piece is here in the series, then it becomes the alternating harmonic series. Let's look at example 2. Example 2, we've got an alternating series. You can see it here in the listing of the terms, and also you can see it here when you look at the general term and you see this -1 to the n. This series diverges by the test for divergence. So if you remember, the test for divergence is the first test that we learned. It also is called the nth term test or the divergence test. And what we can do for this test is we just take the limit of the nth term, right? So we take the limit as n approaches infinity of -1 to the n times n. Now this, of course, just alternates between plus and minus, because whenever there's an odd term, it'll be a -1, an even term will be a +1, and this is just going towards infinity. So what's going to happen is, whenever you have an even term, like when n is even, it's just going to be 1, and then this is going to get bigger and bigger and bigger, right? When you have an odd term, this will be a -1, and this will be getting bigger negative. So what you really have here is this. You've got the even terms of this series are going to approach infinity, whereas the odd terms are going to approach negative infinity. So the limit doesn't exist, because the terms, for the limit to exist, the terms would have to be approaching one particular number. Here they're going off to infinity in two different directions. So we could say, therefore, the limit as n approaches infinity of -1 to the n times n does not exist, right? The limit does not exist because it doesn't approach any one number. It just shoots off towards infinity in one direction, negative infinity in the other direction, so the limit doesn't exist. So by the test for divergence, this series diverges. And then if you notice, the nth term of an alternating series is one of the form like this, -1 to the n plus 1 times b sub n, or it could be like this, -1 to the n minus 1 b sub n, or it could even be like this, -1 to the n. Just all of these cases have the same effect of alternating the positive and negative signs throughout the terms of the series. Also, something that we'll see a lot is this b sub n would be some positive number, so that b sub n is just the absolute value of a sub n, which makes sense, right? This b sub n, if you take the absolute value of this whole thing, this just ends up being 1, right? So you just get b sub n. So b sub n is the absolute value of a sub n. Well, actually, as it turns out, if the terms of an alternating series decrease towards 0 in absolute value, so if you wrap them in absolute value and they decrease towards 0, then the series converges. And this is shown to be the case by Leibniz a while ago in 1705. This is going to be the basis of the alternating series test. We just have to show that these series, if we wrap them in absolute value, they decrease towards 0. So what we can do is take a look in this box here. We have the alternating series test, sometimes known as Leibniz theorem, but usually just called the alternating series test. So first, it requires an alternating series, of course. So you have this series like this. And so we've got -1 to the n plus 1. And of course, this could say n minus 1 also. It doesn't matter, right? It could even say n. It's just some way to make these alternate between positive and negative. So b sub 1 minus b sub 2 plus b sub 3 and so forth. And we've got two conditions to satisfy. One is something that we've seen before, or some variation of this. Basically, this just means that the terms are decreasing. So b sub 7 is greater than or equal to b sub 8. And that applies for any n, right? This term is greater than or equal to the next term, so the terms are decreasing. The other thing we need to show is that the limit as n approaches infinity of b sub n equals 0. If these two conditions are met, then the alternating series is convergent. There's a little note here. In some cases, we may have to use the other technique here. So this is one way to show the terms are decreasing, but if we don't have an easier series, then we may need to find the derivative of the corresponding function to show the terms are decreasing. Okay, so that was like, if you remember in section 11.3, when we were doing the integral test, we had to show that a function was decreasing. So what we did is we found the derivative and just showed where the derivative was negative. So sometimes we may need to do that too to show this decreasing, but normally we can just do this and it's not too bad. So, okay, let's take a look and try this out. So we've got this alternating harmonic series, which we looked at earlier. And we said it's just like the harmonic series, but the signs alternate. So to show that the terms are decreasing, right? We have to show the terms are decreasing. So in other words, b sub 3 is greater than or equal to b sub 4, right? The fourth term. The third term is greater than the fourth term. We have to show that holds for all terms. So I can't just plug in a number here, right? I need to show that it holds generally. Okay, also just to make a note here, this whole thing here is a sub n, right? This whole general term is a sub n. But we need to remember this. The note is that a sub n is -1 to the n plus 1 over n. But remember that b sub n is the absolute value of a sub n. So b sub n is just 1 over n. So whenever we do the alternating harmonic, or when we do the alternating series test, these b's down here are just the absolute value of this term, right? So we're going to do that all the time. B sub n just removes this -1 to the n plus 1 part. So b sub n here is just 1 over n. And that's what we're going to be using here. So if I want to show that the terms are decreasing in absolute value, right? They're decreasing in absolute value. I just need to use the absolute value of a sub n. And then this is easy, because if b sub n is 1 over n, I'm going to replace this n with an n plus 1, right? So I could say this. B sub n plus 1 is equal to 1 over n plus 1. And I'm going to write over here what b sub n is. And when you look at this, you can see between these two, they both have a numerator of 1. This is b sub n right here. This is b sub n plus 1. Since this denominator is bigger, it means that this term is smaller than this term. Right? So we can say less than or equal to, and it'll be true for any n. So we've shown that the terms are decreasing, right? Terms are decreasing, so I can put a little check here. We're good with that. Step 2, we need to show that the limit as n approaches infinity of b sub n equals 0. So that one's easy enough. The limit as n approaches infinity of b sub n is the limit as n approaches infinity of 1 over n, and clearly that is 0, right? It's a Calc 1 problem. As n gets bigger and bigger and bigger, it approaches infinity. Have 1 divided by a giant number. We can make this as close to 0 as we want just by making n big enough so that the limiting value of this is 0. Okay, so we've satisfied the two conditions of the alternating series test, which means therefore the alternating harmonic series converges by the alternating series test. All right, let's look at example 4. We've got another one. Test the series for convergence or divergence. Well, first I'm just gonna look at the second condition. Okay, before we even start thinking about decreasing, just as you do more of these, you'll notice something about some of them. So I'm just gonna write something here. All right, software. Okay, here we go. Notice that. Okay, so b sub n, which is the absolute value of a sub n. So this whole thing is a sub n, right? B sub n is the absolute value of that, so it will remove this. So this little part here is b sub n. All right, so notice that the limit is n approaches infinity of b sub n. Okay, so I'm looking at the second condition of the alternating series test. This is the limit as n approaches infinity of the square root of n over 1 plus 2 times the square root of n. Okay, so back in the Calc 1 days, the good old days of Calc 1, we would have a limit like this. We'd see this is infinity over infinity. So we could use L'Hopital's rule, or the way we first did it is we would say divide everything by the highest power in the denominator, which algebraically is equivalent to multiplying by 1 in this form, right? Because won't this basically divide every term by the square root of n, which is the highest power in the denominator? So when I multiply this through, I'm going to get this is equal to the limit as n approaches infinity. So in the numerator, I'm just going to have 1. The denominator, this will distribute through here, right? So I'll get 1 over the square root of n plus 2, because when you multiply these through, the square root of n's will cancel, so you're just left with 2. And now we can take the limit here. If I take the limit here, I can make this term as close to 0 as we want. So the limiting value of this term is 0. So we just get, once you take the limit, we get 1 over 2, which is not equal to 0. Which means condition 2 is not satisfied. Okay, and whenever condition 2 is not satisfied, essentially that means that the series diverges by the test for divergence. So I'm going to say, therefore, the series diverges by the test for divergence. Because remember, the test for divergence says we could just take the limit of a sub n, this whole thing, and if we don't get 0, the series diverges. Now, we just took the limit of b sub n, but all that means is that since this is going to 1/2, if I include this part, it just means that some of the terms are going to go to 1/2, some of the terms are going to go to negative 1/2, but they're going to two different places. And if you look at it, if I put an odd term like 1, I'm going to get a negative here. An even term like 2, I'm going to get a positive here. So really what's happening, we don't actually have to write this down what I'm going to write here, but I'll write it just so we see. It diverges since the odd terms approach negative 1/2, and the even terms, they approach positive 1/2. Right, therefore the limit as n approaches infinity of a sub n does not exist. The limit doesn't exist because for it to exist, all the terms have to approach 1 and only one number, right? So the limit of as n approaches infinity of a sub n does not exist. But really all we need to do when we do the alternating series test, if you show condition 2 is not satisfied, then basically that means that the series diverges by the test for divergence, right? It diverges by the test for divergence, and we're done. We don't have to look at condition 1 because we already know it diverges. Okay, how's everybody doing? Everybody hanging in there? 11.5 is longer than it used to be. The 8th edition of the book had 11.5 and 11.6 are about the same size because absolute convergence was in 11.6. But the 9th edition moved it around a little, so 11.5 is pretty big, and 11.6 is kind of a small section now. So it covers the same information, just rearranged it a little bit. But one of the things that we can do when we have alternating series is we can estimate the sums. So we've got a partial sum. Remember partial sums, like the sum of the first n terms. So partial sum of any convergent series can be used as an approximation to the total sum S, the total sum of the series. But this isn't helpful unless we can estimate the accuracy of the approximation. So notice that the actual sum is equal to the partial sum of the first n terms plus the remainder, whatever's left after we added up the first n terms, right? So the remainder is kind of like the error. You can think of the remainder as the error. So we've got the actual sum. If we were to add all the infinite terms together, we would get this. But if we have a finite number of terms, we have the sum of the first, let's say, 15 terms, plus the remainder after adding the first 15 terms, right? So the remainder is like the little error. It's the gap between these two. So R sub n is remainder after taking the nth partial sum. So if we use S sub n to approximate S, the actual sum, the error will be the remainder. So then we just algebraically just solve this equation for R sub n and you get this. So again, the error the remainder is the error. So the error is just the actual sum minus the partial sum, right? The little gap between the actual sum and the partial sum, that's the remainder. And we've got an estimation theorem. So the following theorem says that for the series that satisfy the conditions of the alternating series test, in other words, those two conditions, right? It's decreasing and the limit of b sub n is 0. The size of the error is smaller than b sub n plus 1, which is the absolute value of the first neglected term. Okay, so what does all that mean? Let's take a look. The alternating series estimation theorem says this. We've got S, the sum of this series, right? So S is the sum of the alternating series that satisfies these two conditions, right? It's decreasing and the limit of b sub n is 0. In other words, it satisfies those two conditions of the alternating series test. Then we've got this. So let me just mention a couple of things. So this just means we've got, we could say, i.e., a converging alternating series. Right, it satisfied those conditions, so we have a converging alternating series. What this says, we've got this little formula about the remainder. It just says that the remainder is smaller than the first neglected term. So the actual sum minus the nth partial sum is smaller than this first neglected term. Okay? And there's a little note here. The note is that this only applies, okay, this doesn't always apply, it only applies to alternating series that satisfy one and two of the alternating series test. In other words, it satisfies those two conditions, which is basically saying right here. Okay, so if the alternating series, if it diverges, this doesn't apply. Only to converging alternating series does this apply. And we've got a little picture which we can call the geometric verification of this alternating series estimation theorem. It's not a proof, but it just makes it, gives a picture of what's happening, and it makes this seem very likely to be true. So let's take a look at that. Okay, so let's say I start here at 0, and I'm going to add my first term, b sub 1, right? I'm going to add b sub 1 to 0. So let's say b sub 1 is some number, so I'm just going to make it go over here, and let's say it goes over to s sub 1, right? So I'm going to make a little line up here. You'll see why I'm making these lines in a second here. So what I do is I take b sub 1 and I add it to 0. So the first term of the series is b sub 1, and that brings us over to here on the number line s sub 1, right? This is b sub 1 is the first term of the series, and s sub 1 is the sum of the first term, okay? Now, since this is alternating, b sub 2 is going to be negative, right? If b sub 1 is positive, b sub 2 is negative. So if I add that to b sub 1, I go b sub 1 minus b sub 2, it's going to bring that back over here, right? So let's say then I subtract b sub 2, and it takes me over here. Okay, and right here, I've got minus b sub 2, and this brings me to s sub 2. So this is the sum of the first term. S sub 2 is the sum of the first two terms, right? Because b sub 2 was negative, so it brought us back. Now, since it's alternating, b sub 3 is going to be a positive number. So if I take the sum of the first two terms and I add b sub 3, it's going to go over this way because b sub 3 is going to be positive. Also, since these have to get smaller and smaller, b sub 3 is going to be smaller in magnitude than b sub 2. So now I add b sub 3, that brings us over here, and now I've got s sub 3, the sum of the first three terms, right? So then maybe I'm going to subtract b sub 4, it's going to be a negative. The fourth term will be negative, so when we add that to s sub 3, it brings us back over in this direction. So now this is minus b sub 4, and this brings me to s sub 4. So the sum of the first four terms is here. You can see it looks like we're heading in towards here, right? So let's say do it one more time. So the fifth term would be positive, so I add the fifth term. It brings us over here somewhere. Again, because these get smaller and smaller, we know that b sub 5 is not going to go past here because it's got to be smaller than b sub 4, right? Because they decrease in absolute value. So then over here you can see this is going to be the sum of the first five terms. And what's going to happen is we could go further and further. You know, we're just going to keep going back here and then back here. And we're going to get, you know, this will be s sub 6, this will be s sub 7. But basically we're going to go back and forth, and we're going to get closer and closer and closer to the actual sum, s. So all the even terms are heading here. All the odd terms are headed here. So everything's heading towards the actual sum s. And you can notice a few things. So here's something to notice about this one. Here's where the alternating series estimation theorem will start to make sense. So the magnitude, the difference between s and s sub 2 is going to be less than b sub 3, the first neglected term. So let's look at the difference between the actual sum and s sub 2. Here's the actual sum, and here's s sub 2. The difference between these two, this distance, is going to be less than b sub 3, which it is because here's b sub 3, right? B sub 3 is bigger than that. So the error here, the difference between the actual sum and the partial sum of the first two terms, is less than the size of b sub 3. And we could do it one more. Let's go like s minus s sub 3. That's going to be less than b sub 4. So the magnitude, right, absolute value or distance between this actual sum and s sub 3. Okay, here's s sub 3. The distance between these 2 points is going to be less than b sub 4, which it is because look at b sub 4. is this distance, right? And this keeps on going. So basically, these are the errors, right? The remainders. The error is less than the sum of the first neglected term, and this just keeps on going. So it's just a little picture of that alternating series estimation theorem. Makes it seem reasonable. So now that you've seen the alternating series estimation theorem in a box, I know what you're thinking. You're probably thinking, sure would like to try out our new theorem. Well, you are in luck because we've got a couple problems here that will allow us to try this out. So example 5 says, show that the series is convergent. So we want to first show it's convergent. Then they ask, how many terms of the series do we need to add in order to find the sum to the indicated accuracy? Okay, so the error, the magnitude of the error, absolute value of the error, would be less than 0.0001. Okay, now we also know this. We also know that the error will be smaller than the first neglected term. Right, and we know that because of the theorem we were just talking about. So, all right, first let's notice something here. This whole thing is a sub n, right? That whole thing is a sub n. So b sub n is the absolute value of a sub n, which is basically just 1 over n times 5 to the n, right? So that's b sub n. So let's check these conditions for the alternating series test. First one, b sub n plus 1. If I replace the n's with n plus 1, I get 1 over n plus 1 times 5 to the n plus 1. Now if I compare that to b sub n, we can see that the denominator here is bigger than the denominator here. Numerators are exactly the same. So if the denominator is bigger, it means this is smaller, right? Just like if I have an example, 1 over 1,000 compared to 1 over 10, the larger denominator makes a smaller number, right? So that means that we have an inequality going this way. So we can say that this is less than that. So in other words, the terms are decreasing in absolute value. So condition 1 is satisfied. Condition 2, we have to take the limit as n approaches infinity of b sub n, which is the limit as n approaches infinity of 1 over n times 5 to the n. And if n gets bigger and bigger and bigger, that will approach 0. So the limiting value is 0. So we're good there. So we can say, therefore, the series is convergent by the alternating series test. Okay, so we've shown it's convergent. Now they want us to figure out how many terms of the series do we need to add in order to find the sum to the indicated accuracy. So for that part, let's write this down. N equals 1 to infinity, negative 1 to the n over n times 5 to the n. And these are going to be easy. Usually the easier way to go is just to list these out. So if I let n be 1, I'm going to get a negative number, right? Because I'll get negative 1 to the n, so I'll get negative 1. And down here, I'm just going to have 1/5, right? Plug a 1 in here, get 1. 5 to the n is just 1, and this makes it negative 1 to the n, which is a negative. Now if I plug a 2 in there, I'm going to get 2 times 5 squared. This will be a positive, so it'll be a plus. So you get plus 1 over 2 times 5 squared. Then I plug a 3 in there, it'll be negative again, 1 over 3 times 5 cubed. And let's do 2 more. Plug a 4 in there, I'll get 1 over 4 times 5 to the 4th. And 1 more, get 1 over 5 times 5 to the 5th. Okay. But what we want to see is, when will our first neglected term be less than this, right? So I'm just going to look at I'm going to look at this one. So if I punch this number into the calculator, 1 divided by, and then in parentheses, 4 times 5 to the 4th, what I get here, 0.0004. Okay, I'm not quite there yet. So I need this term. Let's try this one. If I punch this one into the calculator, what I get for this one is 0.000064. Okay, this one is too small to affect the answer since, let's just see, since 0.000064 is less than 0.0001. Okay, so we don't need that one. So we should just need 4 terms. So if I add up these first 4 terms, the answer to the question, we need 4 terms. So the answer is 4. And then if we add those up, we get about this. So we get this is approximately equal to negative 0.1823. S sub 4 is equal to negative 0.1823. Okay, so we need 4 terms to have an error less than this. So something like this, just easier, show that the series is convergent, and then we can just add up some terms until this condition is met. So, all right. Fun stuff, right? We've got one more, though. One more like this. So let's take a look at this next one, example 6. Approximate the sum of the series correct to 4 decimal places. So I'm just showing you 2 different ways that the book will ask kind of the same question, 4 decimal places. So what this means when they say this means keep adding terms until the 4th decimal place doesn't change. Okay, so that's what we've got to do. So, okay, this one is equal to, if I plug in a 1, I'm going to get negative 1 over 3. Right, plug in a 1 here makes it negative. This would be 3 times 1 factorial, which is 3. Remember, factorials are just numbers, if you have like 5 factorial, it's just 5 times 4 times 3 times 2 times 1, right? You just start at this number and go back by 1, and you always multiply. Right, so 5 factorial, 0 factorial is by definition equal to 1. That might be one that's a little strange, but that's just by definition. Sort of like x to the 0 power is 1 by definition, same sort of thing. Okay, so those are factorials. So let's see, it's going to be plus 1 over 3 squared times 2 factorial. Now on your calculator, if you use a TI-83 or 84, the factorials, if you press the math button, far left column on your calculator, press math, and then scroll over to the PRB, probability, and you can see the 4th one down. It looks like an exclamation point, it's factorial. So on the calculator, if you wanted to find that 5 factorial, you press 5 first, and then go to math, probability, factorial, and hit enter, and then it'll give you the answer. Okay, so that's how you find it on the TI-83, 84. But all right, let's keep going here. So then we've got minus, I plug in a 3, I'm going to get 1, 3 cubed times 3 factorial, plus 1 over 3 to the 4th times 4 factorial, minus 1 over 3 to the 5th times 5 factorial. I'm going to put 1 more. 1 over 3 to the 6th times 6 factorial. Okay, so what we've got here, negative 1/3 plus 1 over 18 minus 1 over 162. I'm just letting the calculator do the work here on these. And then plus 1 over 1944. So 4 decimal places. So these aren't really getting super tiny yet. But I may have spoke too soon. They're starting to get tiny now. 29,160 plus 1 over 524,880. Okay, so now let's start adding these up and see what we get. Okay, so if I add up, let's say the first 4 terms, so it would give me S sub 4, right? The sum of the first 4 terms. I get negative 0.2834. So what I need to do is now add up one more term and see if that 4th decimal place changes. So the sum of the first 5 terms, if I add all those up, I get negative 0.2835. Okay, so it's still changed, so I'm going to need to add at least one. I need to keep adding until that 4th decimal place doesn't change. Okay, so let's add one more. So I'll add these first 6 terms up. So I'm going to scoop this one up now. S sub 6, when you add those, finally we get no change. Okay, so remember, because these terms are getting smaller and smaller and smaller, right, by the conditions of the alternating series test, I know I'm not going to add something that's going to change this one suddenly. Like suddenly I'm not going to get like 1/2 where it changes this, right? These get smaller and smaller and smaller. So once it stops changing, it's not going to start changing. It's done. So adding B sub 6, right? The 6th term didn't change S sub 5 to the 4th decimal place. It changed it, but not to the 4th decimal place. So this sum then is the answer correct to 4 decimal places. This is the answer we're looking for. And you can do this one on the calculator too. I'll show you. It's a little bit quicker. So there's on the next page here, we go over how to do this on the calculator. And you don't really have to do this. This is just a little bit extra if you want to. If you have on the TI-83 or 84, you press the second button and then go to stat. And that when you go second stat, it brings up it brings up a menu for, it says names, ops, and math. So you go second stat, and then you want to go to the math menu. And from the math menu, you just select 5, which is sum. Again, you don't have to do this. This just makes it a little easier if you want to. You can kind of play around with this. But when you press 5 sum, then from there, from this spot, you go to second stat again. So you go second stat. This time go to the ops menu. And then pick 5 again, but this time it'll be for a sequence. Okay, now when you do that, there's a couple versions of the software. The newer version will give you this. Like this will just appear. This is just to fill in the blank that will then paste in. So if you don't have this, it's okay. I'll tell you what to do in a second here if you don't have this. But if you do have this, what we want to do is go down to here. For those of you who have this showing, the expression here is basically that expression that we just had. So it's from the last example, example 6. So the expression you want to put -1 raised to the x. And remember to find the x, you just press the key that says x, comma, t, comma, theta, comma, n, and that x will appear. And then you go divided by parenthesis 3 raised to the x, and then times x, and then factorial, close parentheses. So that's right here. It's actually right here too. You can see it right here. Okay, but when you do the screenshot, it doesn't show the whole thing. But basically, just type in this right here. Of course, just this part of it here. Okay, so type that in here just like this. The variable is just x, so we want to, when you go down to the variable, press x, the same x that you had right here. And then we're going to start at 1, we're going to end at 4, and the step size will be 1, then you hit paste. And then once you do that, you'll see this screen. Okay. Now, if you have the older software, you just want to type it in just like this. So the older software doesn't have this screen. So it'll just say sum of sequence, and then you just punch it in like this. And when you hit enter, you're going to see this is the sum of the first 4 terms. So you hit enter, and this number comes up. But then maybe you want to go to the sum of the first 5 terms. So when you do this command here, when you do second enter, it'll bring up the previous command, and it allows you to edit it. So right after this, just press second enter, and this will come up again. And now you can move the cursor over to the 4 and change it to a 5. And then hit enter, and it gives you this. So again, this is optional. You don't have to do this, but it's I don't even know if it's quicker to do this because there's a lot of stuff to type in the calculator, but it's something you can play around with, and you can do some of these problems. You can check them on your calculator like this. Okay, and this brings us to the last thing that's covered in this section, which used to be covered in 11.6, but it's in 11.5 now. This is absolute convergence. So to get started, we've got a series listed here, kind of strange looking, but got 24 and then negative 3/4 raised to the n minus 1. And if you just start plugging in numbers here, if I plug in a 1 in here, I'm going to get this to the 0, which is 1. So I just have 24 times 1. So I have 24. And if you start plugging in, you know, keep going, plug in a 2 and then a 3, we end up with this right here. Okay, so you can see by looking at the way it's set up, this is an alternating series, right? Because this right here is going to alternate. It's going to flip-flop between positive and negative. But it's also geometric. You can see right here, it's a geometric series, right? With r equal to negative 3/4. So remember, from geometric series, if the absolute value of r is less than 1, it converges, right? And it converges to a over 1 minus r. This is from section 11.2, where a is the first term of the series. So its sum is going to be, well, we can go 24 divided by 1 minus 3/4, which is 24 over 7/4, right? Which is equal to 96 over 7. Okay, so this particular alternating series is a geometric series, and the sum is 96 over 7. But example 8 takes the same series and wraps it up in absolute values. Once you wrap this up in absolute values, then you're going to get the same numbers, but they're all going to be positive. Right, so it's the same numbers, but they're positive. So now it's a geometric series. If you look at this right here, you can see it's a geometric series with r equals positive 3/4. So I equals positive 3/4. Thus, it converges to 24 over 1 minus 3/4, which is 24 over 1/4, which is 96. And this leads us to what's called absolute convergence. So a series is said to be absolutely convergent if its corresponding series, let's say n equals 1 to infinity, of a sub n wrapped up in absolute values converges. So that's what happened. We took the previous series and we wrapped up an absolute value and it converged. So because of that, this series is called absolutely convergent. The original series that we looked at would be called absolutely convergent because its corresponding series wrapped up in absolute value converged. It turns out that absolute convergence implies convergence. So any series that is absolutely convergent is also convergent. Now this should make sense because think about it. If I take a series and put it all absolute values, so it's all positive numbers, and it still adds up to a number, right? It doesn't go to infinity. Well, then if I made some of the terms negative, it seems like that would also converge, right? Like it'd be unusual. I mean, it just in your mind, it would seem strange if I add up a bunch of positive numbers, I get a number, right? Not infinity, but a number. And then suddenly I make some of them negative and all of a sudden I get infinity or something, right? It just doesn't seem, or negative infinity doesn't seem reasonable. So this does seem reasonable. Any series that is absolutely convergent is also convergent. All right, so with that in mind, let's check out example number 9, which says consider the alternating harmonic series, which we've seen. N equals 1 to infinity, negative 1 to the n minus 1 over n, which equals 1 minus 1/2 plus 1/3 minus 1/4 plus ... We've seen this one before. And notice that b sub n plus 1 is less than or equal to b sub n because b sub n plus 1 equals, remember now, b sub n is the absolute value of a sub n. This whole thing is a sub n. B sub n is the absolute value of that, which should just be 1 over n. This part just pretty much turns into 1, right? So b sub n is going to be 1 over n plus 1, which is less than or equal to 1 over n, which is equal to b sub n. So the terms are decreasing. And then the limit of b sub n is equal to the limit as n approaches infinity, 1 over n, which equals 0. So the limit of b sub n is 0. So by the alternating series test, this series converges, okay? Which we've seen already. But what we're going to do now is we're going to take that same series and wrap it up in absolute values, right? So we had this series here. We're going to wrap this up in absolute value. And then let's see what happens. Okay, we wrap it in absolute value and all the negatives go away. So you get 1 plus 1/2 plus 1/3 plus 1/4 plus ... All right, and we know that this series is the harmonic series. This series diverges by the p-series test. P equals 1. Because this is basically, if you look at what these are doing, it's n equals 1 to infinity, 1 over n to the p. And the p-series converges if p is greater than 1, but it diverges if p is less than or equal to 1. So this one diverges. So what we have is this. This series converges, but once we wrap it up in absolute values, then it diverges. So this is said to be conditionally convergent. So if a series converges, right, so the regular series converges, but I wrap it up in absolute values and it diverges, then the series is said to be conditionally convergent. Okay, so again, the series converges. By itself it converges, but when I wrap it up in absolute value, then it diverges. So then it's called conditionally convergent. Okay, so just a couple of terms. We had absolute convergence, which means the series converges, and if I wrap it up in absolute values, that converges also. But conditional convergence means the series converges, but I wrap it up in absolute values, then it diverges, then it's conditionally convergent, okay? So this last one is kind of a strange series, okay? It's, if you start plugging in numbers here, okay, something kind of strange happens because of the cosine value. So what you'll get, plug numbers in here, as far as positive and negative goes, you'll get negative, and then negative, and then positive, and then negative, and then you get a positive and a negative. So basically the idea is it's not an alternating series, right? This is, by looking at this, we can see this is not an alternating series. Okay, well, let's first consider, this is kind of an unusual one. Let's consider, because of that cosine, what if I were to take this thing, put in absolute values. Because we know something about the cosine graph. Isn't the cosine function trapped between -1 and 1? Right? Sine and cosine are both trapped between -1 and 1. That's absolute value there. So let's note that cosine of 4n is less than or equal to 1, right? I can plug anything I want in here, but if I input into the cosine function, it's stuck between -1 and 1, right? The range of cosine is -1 to 1. So no matter what I plug in here, it's going to be less than or equal to 1. Right? So therefore, we could say cosine of 4n over n to the 4th wrapped up in absolute value is less than or equal to 1 over n to the 4th because this is less than or equal to 1. Right? Less than or equal to 1, so we could say that when I wrap this up in absolute value, it's going to be less than or equal to 1 over n to the 4th. So that means we can maybe do a comparison test here. So what about this? What about the series n equals 1 to infinity, 1 over n to the 4th. Now we know this is a convergent p-series. Convergent p-series is p equals 4, which is greater than 1. So this is a convergent p-series, and it's greater than or equal to this. So this thing adds up to a number. We don't know what it is, but we know it converges, so it adds up to a number, and it's bigger than this one. So that means this one also has to converge, right? By the comparison test, we can say, so by the comparison test, n equals 1 to infinity of the absolute value of cosine of 4n over n to the 4th also converges. Remember, we also know that absolute convergence implies convergence. So in other words, if I take a series and I wrap it up in absolute value and it converges, that means the original series also converges. Right? So then we could say, thus, our original series, cosine of 4n over n to the 4th, must converge. Because absolute convergence implies convergence. I took this series, put absolute values in here, so then we could make a comparison. And if you wrap up a series so that you get nothing but positive values coming out, and it converges, meaning you add up all those positive values, you get a number, well then it only makes sense that the original series, which will have alternating positive and negative numbers, if you add those up, they'll also add up to a number that will just be smaller than this number, right? So we took the absolute value of the series and it converged, therefore the original series must converge. All right, and then finally, there's a little interesting fact here. The Riemann series theorem says by a suitable rearrangement of terms, a conditionally convergent series may be made to converge to any desired value whatsoever. And it's kind of surprising, but they talk about it a little bit in the book on page 772. So if you are interested in looking into that more, you can take a look at that. Okay, but that gets us through 11.5. So we're close to being done with the series test. We've got a couple more to look at in 11.6, and then we will have seen all of the series tests. So go ahead and give this one a try. And if you have any questions, make sure to let me know. And I will talk to you soon.